All right, welcome to worksheet 16. This is a summary of curve sketching. This section corresponds to section 3.5 in the book. Basically, we're going to incorporate what we learned so far and then use it to graph given function. So let's kind of summarize what we have so far. And there are some new things, but these are a few things that we want to kind of consider when we try to graph a function. So without calculus, what we're going to do, first thing we're going to look at is domain. So some of them might be just a review. Domain is all possible x values, right? All possible x values that function takes in, that f of x takes in, takes in. So mostly is all x, all real number x. Few things, if you have a square root of x or fourth root of x, so on and so forth, then x has to be bigger than or equal to 0. If you have like 1 over x, obviously x cannot be 0. So there are a few things we can't, there are a few values that we cannot, certain functions cannot take in. Otherwise, all x's. Intercepts, there's x-intercept, there's y-intercept. X-intercept is where the graph goes through x-axis. So this is, we let y to be 0 to find it, right? And then vice versa, y-intercept will let x to be 0 to find it. This is where the graph goes through either x-axis or y-axis. Third thing we can find is asymptotes. Asymptotes. So we have a vertical asymptote and then we have a horizontal asymptote, right? So horizontal asymptote, HA for horizontal. That's when we take the limit as f of x goes to, as x goes to infinity, or limit as f of x as x goes to negative infinity. If you get a particular number, then that's where we have a horizontal asymptote. So we get it when it's like some number. Sometimes the limit doesn't exist, then we don't have a horizontal asymptote. If the limit exists as x goes to infinity or negative infinity, then whatever the number is going to be our horizontal asymptote. Next one is vertical asymptote. Vertical. That's when we have basically happens at x is equal to c if the limit as x approaches to c from the right hand side or from the left hand side, and limit of f of x as x approaches from c from the left hand side is either positive infinity or negative infinity. All right, so a lot of times when we have a fraction or when you have a denominator, when the denominator goes to 0, that's possibly we can have a vertical asymptote. And we have the slant asymptote or diagonal. We don't really talk about it too much. Now let's look at number 4. Another interesting aspect of a graph we can think of it is symmetry. Symmetry. There are few, we can kind of categorize in a few different ways. Even function. Symmetry just means like one part of the graph looks exactly like the other part. So even function, for example, like f of x is like x squared or x to the fourth, so on and so forth. The property of even function is when you have f of negative x, it's basically the same as f of x. For example, if you look at x squared, right? Like negative x squared is the same thing as x squared, right? So what that means is when you input like negative number, it's exactly the same as inputting a positive number, right? Because when you square it, you both get the positive answer. And same for negative x to the fourth power is the same thing as x to the fourth power, so on and so forth. The reason it's called even function is any even power will give you that property. If you look at the graph of even function, you basically, whatever, this is not the graph of x squared, but whatever happens on the left side of the graph looks exactly like whatever happens to the right hand side of the graph. So that's why it's a mirror image. That's why it has a symmetry. It's even function. Odd function has different type of symmetry. Odd function, for example, f of x is x or x to the third power, x to the fifth power, odd function. The property is red here. the property is f of negative x is equal to negative f of x. What that means is, let's say negative x to the cube is basically negative x cubed, right? It's like, okay, it's not saying really much. So in terms of graph, basically it's symmetry around about the origin. So graph looks like here, and then the other graph looks like this. So it's symmetry this way, like to the whatever happens here, you go through the origin and then you get something else on the other part. So that's even function and an odd function, right? And then we also have a periodic function. Oh, we have sine and cosine and all that stuff, right? So sine x, cosine x. Actually, in terms of evenness and oddness, cosine x is one of the even function, and then sine x is one of the odd function. Okay, so those are things we could have done without, we can do with no calculus at all, no derivatives and stuff. What can we do with calculus? First thing we can do is basically we look at the derivative and see when f is increasing or decreasing, right? F prime is bigger than or equal to 0 when it's increasing, F prime of less than or equal to 0 when it's decreasing, right? So we don't allow those. We can also look at when F has local max or local min. So basically if you have something like, if function is increasing and function is decreasing, this is local max. When function is decreasing, when function is increasing, this is local min. So graphically kind of makes sense. Different color there. We can change the concavity. Another thing, concavity has inflection point. Here, concavity is second derivative is positive. That means it's concave up. That means you're part of the happy face. If second derivative is negative, then it's concave down. That means you're part of the sad face, right? Inflection point is when the concavity changes, right? So those are what we've talked about in previous sections. All right, let's look at some examples here. Let's look at the first example. Sketch that graph, and they're asking domain, intercept, everything we kind of talked about. So domain, this is polynomial. You can basically, there's no like 1 over x, there's no square root of x, it's just polynomial. So domain is all real numbers. So negative infinity to positive infinity. Intercepts, plug in x is equal to 0 for y-intercept. So if you plug in 0 here, 0, 0, 0, negative 5. So y is equal to negative 5. So 0, negative 5 is the x-intercept. I'm sorry, y-intercept. Intercept. And then x-intercept is you plug in y is equal to 0 for x-intercept. 0 is equal to 2x cubed minus x plus 12x minus 5. Generally speaking, we do not know how to solve. It's kind of hard to solve cubic polynomial. Here I can kind of give you a hint where I kind of know the answer. So 1 and 5 over 2. So that means 1. When I plug in 1, you're going to get 0 as a y. Also, when I plug in 5 over 2, you get 0. So these are my x-intercepts. So what that means is, if I kind of look at the graph, our y-intercept was 0, negative 5. So I can go here, 0, negative 5 is my y-intercept. And then x-intercept was, what was my x-intercept? 1 and 5 over 2. So 1, which is here, and then 5 over 2 is basically 2.5, so over here. So again, I don't know how the graph looks like, but it goes through this point, and this point. So that kind of gives you an idea how the graph is going to look like. Let's go back to the symmetry. Here I'm looking at third power, so that's like, oh, it's an odd function, but then there's an even power, so okay, it's an even function. When you have odd function plus even function, it's basically nothing. if I didn't have this power, if I didn't have this power, this number, then it will be odd function, and vice versa. But here odd function and even function are added, so no symmetry. So no symmetry. Asymptotes. For horizontal asymptote, we have to take the limit as x goes to infinity. So let's see, limit as x goes to infinity of 2x cubed. Let's just call it f of x. F of x. Here, it's just polynomial, so just go to infinity. So it's not a particular number. It's not a number. It's infinity, right? So no. And then if you let x to go to negative infinity, it goes to negative infinity because it's determined by the highest power. So that's negative infinity. So no horizontal asymptote. And vertical asymptote doesn't exist either. I don't have like a zero denominator. So no vertical asymptote. No vertical asymptote. We don't have zero denominator. Because that's possibilities for having a vertical asymptote. We don't have that. Let's look at the first derivative to figure out when it's increasing or decreasing. So f prime of x is going to be 6x squared minus 18x plus 12. So I'm going to set that equal to 0. That's when you have a horizontal tangent line. So that means your function is not increasing. That's basically your critical point. So I can factor out 6x squared minus 3x plus 2. I can do x minus 1, x minus 2 is equal to 0. So that means x is equal to 1 and x is equal to 2 is the critical number. So x is 1, x is 2. I want to look at f prime of x to see if it goes up or down, like when does it go up and when does it go. Again, when you have two critical numbers, we have 3 sections, 3 intervals. So this interval, pick a sample number 0, let's say. Plug in 0 here, 0, 0, plus 12, so that's going to be plus. Pick a number here, 1.5. Pick 1.5, plug 1.5 in here. So this is my derivative also. Pick 1.5 here, that's positive. 1.5 minus 2 is negative. Positive times negative is negative. So that's going to be my negative. And then pick some number here, 3. 3 minus 1 is positive. 3 minus 1 is positive. So that'll be positive. So that means f of x is basically increasing, decreasing, increasing. So what I can say is we have local max here and local mean here, right? So here, f of x is increasing from negative infinity to 1 and also 1 to infinity. F of x is decreasing from 1 to 2. And then local max and local min. Local max is when x is equal to 1. So when you plug in x1 into the original equation, plug in 1 here, that's 2 minus, that's 0. F of 1 is equal to 0, so 1, 0. So local max is 0. It happens at x is equal to 1. Local min happens when x is equal to 2. So f of 2 is equal to, so I'm going to plug in 2 into this equation. When you calculate it out, you're going to get negative 1. So 2, negative 1. So this is, local min. All right, so these are all the things I can get, all the information I can get from my first derivative. From there, I know where the function is increasing, function is decreasing. So here, it kind of gives you an idea of like, oh, function is going to go up here, and then it's going to go down, then it's going to go up again after 2, right? So it goes this and this. So I have a general idea how the function is going to look like. Let's look at the second derivative. So first derivative was this thing. Second derivative will look like f double prime of x is 12x minus 18. Again, I want to see when it's positive or negative. So let's say when it's equal to 0 first. I can factor out 6. 2x minus 3 is equal to 0. X is 3 over 2. Right? So here, 3 over 2. Let's look at the second derivative. So again, here I only have one. So I have two intervals. Give me a sample point here, maybe 0. Plug in 0 here. 0 minus 3 is negative. So my second derivative is negative here. Give me a number here, 3 over 2, so like 10. Plug in here, 2 times 10 is 20, that's positive. So that's positive here. So that means my graph is going to be concave down in this interval, and then it's going to be concave up in this interval. Okay, so concave, let me use red, concave down from negative infinity to 3 over 2, concave up from 3 over 2 to infinity. All right, so it's a lot of information, I know. Let's see if I can put it all together. So my function is increasing from here all the way to 1, it increases. But does it increase like this way, like concave up way, or concave down way? Well, according to here, up until 3 over 2 is concave down. So it's increasing concave down like that. So my graph is going to look like this, right? And it says it's decreasing between 1 and 2. So it goes still concave up. But at 1.5, it becomes concave. I'm sorry, still concave down, but at 1.5 it goes concave up, so it kind of switches. There's inflection point right here, so it switches like that, and it goes on the 2. And I just realized I miswrote it here. It should have been negative. It's 2, right? I wrote 1, so I'm gonna change that. It should have been 2 instead of 1. 2 to infinity. So after 2, it goes up again. So, and it's still part of the happy face. So now it goes up like this way. So your graph goes up, down, switch to the happy face, then go up. Right? So I kind of knew the shape of the graph when I saw the points, but I wasn't sure exactly how it was going to go. But by incorporating the first derivative and the second derivative, I can make my graph like very precise. All right, so that was number 1. Number 2, I'm going to have you do by yourself. It's given, your first derivative and the second derivative is given to you. Example 3, also I'm going to have you do by yourself. My hint is the first derivative is f prime is 2 minus 2x to the negative 1/3 power. That means it's 2, 1 minus 1 over radical cube root of x. Again, negative 1/3 power is negative power, so it's 1 over something. 1/3 power means it's cube root. So to find the critical number, just a hint, critical number is when f prime of is equal to 0. So it means 2, 1 minus cube root of x is equal to 0. That means basically 1 minus 1 over cube root of x is equal to 0. That means 1 over cube root of x is equal to 1. That means x is equal to 1, right? Or there's another one. Notice that I have a denominator, so critical number is also when the derivative doesn't exist. This is so when x is equal to 0. So x is equal to 0 is also a critical number. So I have 2 critical numbers to take care of. And that will be my hint for you to kind of guide through this problem. And number 4, yeah, I think you can do that by yourself as well. And for this worksheet, I'm going to have to separately just attach the other graph and then other information about the graph. All right, this is it for this worksheet.